Hey there, here's another screencast, this one on hypothesis testing. Hypothesis testing can be seen as the culmination of the work we've done this semester, and it brings together what we've learned about probability distributions, descriptive statistics, point estimates, and confidence intervals. The tool of hypothesis testing shows us how to use statistics in a way to compare measurements and affirm statistically significant differences. I'm going to show you how hypothesis testing works with an example. So let me talk about this. I commute to work on my bike, pre-COVID anyway, because my car is a 2005 Toyota Land Cruiser, and it has very bad gas mileage. I keep track of my fuel ups and my odometer readings to track my fuel economy because sometimes a mechanical problem can happen and it's not obvious that it's happening, but you can see it or there's evidence of it in your mileage record. 2 years ago, I upgraded my front and rear bumpers, adding about 400 pounds to the truck, at least 400 pounds. So my question is, did that addition appreciably change my fuel economy? So here's the data. Before I changed my bumper, I had about 150 records of fuel ups at the gas station and odometer readings. And those fuel ups showed me, when I calculated the average fuel economy, I had an average of 12.1 miles per gallon. Since I put on the new bumpers, I've went to the gas station about 35 times. And those 35 records show an average fuel economy of 10.7 miles per gallon. And in those 35 records, I've got a standard deviation of 3 miles per gallon. And this isn't unusual. This is a heavy truck. You can have big swings in your fuel economy pretty easily. The driving in the last 2 years, for what it's worth, included all kinds of driving. Freeway driving, side streets, mountains. So it's going to be a good representative sample of the way the truck drives. It's not like it was all mountainous driving or it was all freeway driving. So the question I have is, did the addition of the bumpers make my fuel economy decrease? On the face of it, you can see there's this difference. So a reasonable person would say, well, yeah, it looks different to me. But if you look at the standard deviation, 10.7 plus 3 is bigger than 12.1. So is that within the margin of error? Well, in this class, we've learned how to think about these things, how to work about these things, and so we can put a very fine analytical point on this. So let's do it. What do I expect my fuel economy to be? Well, in these 150 records, well, actually, in the 35 records, that's a large data set. 35 records is large, right? It's bigger than 30. So that's cool. So the central limit theorem says my mean, my sample mean distribution is normal, with mean mu and variance sigma squared. So what are our means and our variance? Well, let's the way you begin is you begin by making an assumption. Let's assume that our average fuel economy is indeed the 12.1. So we're going to assume that the addition of the bumpers didn't make a change. Okay. It's assuming the status quo. It's the accepted fuel economy before the event of adding the bumpers. So we're going to assume that. And then what do we know about sigma squared? Well, we know sigma from our data set is 3. So the question is here, what is sigma bar? Well, we know that for the sample mean, sigma bar is going to look like this. And here we're, not the sample mean, I'm sorry, for the standard deviation. So here we're making an assumption that because our data set is large, our standard deviation is going to be very close to or equal to the sample standard deviation. So we're making that assumption here. Okay, that's because the set is large. And then we know from what we've studied that the standard deviation of the sample mean is the standard deviation of the distribution divided by the square root of the sample size. And we'll just be more explicit. I'm going to say that. Okay, so we've, now we've said our sample mean is distributed normally with a mean of 12.1 and a variance of 9/35. Okay, I'm following what I did here and putting the variance in. Okay, with that assumption in place, we're going to ask, what's the probability that I could take a sample of size 35 and get a sample mean of less than or equal to 10.7, right? That's what I got in my last 35 records. So what is this probability? And so I'm saying, what's the probability of getting this or less? Because if I just put an equal sign here, we know, since my sample mean is a continuous normal distribution, the probability of getting any one specific number is 0. So we talk about intervals, probability of landing in an interval. So what's that probability? Well, let's pull out R. And to calculate this probability, we use the pnorm command. And we're interested in calculating the probability of getting this value or less for a normal distribution that has a mean of 12.1. And then here's where we have to put the standard deviation in. So the standard deviation, 3 over the square root of 35, is 0.570926. You plug that into R and you get the number 0.002888267. So this tells us that under these assumptions, the probability that I get average fuel economy of 10.7 miles per gallon is this. So the chance of that happening is 0.288%. Tiny chance. How does that make me feel? Well, I know the driving I did when I measured that fuel economy was regular or normal driving. So I'd expect to get an average fuel economy that's close to the real average, right? I'd expect my sample mean for these 35 records to be close to my average. Well, if my average were 12.1, I would not expect to get a fuel economy of 10.7. So what do? Because we know we did nothing out of the ordinary, we conclude the mileage must have decreased. So we reject the idea that the mileage is the same, and we say, oh, my average fuel economy must have decreased because I got these new bumpers. Okay. This is kind of like, it has a feeling of a proof by contradiction. You assume something, you go and look at the consequences of that assumption, and you follow those consequences through, and you get a result, and you say, oh, well, that's kind of crazy. And so you say, well, this must be wrong. And because the probability that our sample was so small, that's us seeing, oh, there's evidence to say there's something wrong with this. That assumption was in error. And so we reject that assumption. Okay. and we conclude the mileage must have decreased. So that's how hypothesis testing works. Let me show this to you in a slightly different way. The way we write this down, the special notation and symbology that go along with hypothesis testing is this. So we would write, we have two hypotheses. The first one we write is H naught, and its hypothesis is that our fuel economy is bigger than or equal to 12.1 miles per gallon. And the alternative hypothesis is that the fuel economy is less than 12.1 miles per gallon. So H naught is called the null hypothesis. The null hypothesis represents the status quo. Okay, the way things were before. H1 here is called the alternative hypothesis. And it represents the new state of things. And what we're doing is we're looking for evidence to reject the null hypothesis. That's the technical language that we use. Is there sufficient evidence to reject the null hypothesis? The first thing that we did is we identified the distribution for the sample mean, that it was normal with mean 12 and standard deviation, or variance, we'll say, 9/35. And then we computed what's called a p-value. Of 10.7. That is the probability that our sample mean was less than or equal to 10.7. We got that to be 0.00288. And because the driving was done during these 35 regular measurements, we reject the null hypothesis. In fact, even if you didn't know anything about the conditions under which your sample was generated, this probability is so low you would reject it. So typically, so how do you know if the p-value is small enough for you to reject the null hypothesis? Typically, the threshold for rejecting the null hypothesis is set ahead of time. And typical thresholds are 1%, 5%, 2.5%. And there's no scientific justification for why people set p-values the way they do. Each discipline has a p-value that they like to use. In social science, p-values can be higher. In engineering, p-values should be lower. Yeah, but that's what you need to know. If you're working a problem, Generally, you'll know ahead of time what p-value to use to evaluate the null hypothesis, and helps you decide whether or not you reject the null hypothesis. If this p-value had been bigger, I would say there is insufficient evidence to reject the null hypothesis. Instead of saying that, I'd say there's insufficient evidence. Okay, so this is your introduction to hypothesis tests. The textbook is really good, has a really good discussion on this stuff. I just wanted to give you something that looked a little different, and put my own little spin on it. I'll do some more examples in class and do some screencasts too. All right, see you next time.